important topic, and which is the last topic for this chapter, and that is the potential energy. Potential energy in physics, we denote it by a symbol of U. Okay. Now, so far we have seen that for a point charge, okay, for a point charge we have the terms like electric field. We have a term like the potential. Like at this point, say at a distance of r, what is the electric field at this point? Electric field is equal to kq by r, isn't it? R square, sorry. And at this point we also have another character which is known as a potential, and we q by r. So these are the things we have discussed. Now for a point charge, what is the potential? Potential is not defined for single charge. Okay, so the potential of a single charge is zero, though it can have electric field, it can have potential at different points. However, the potential of a charge at any point is zero for a single charge. Okay, because potential is undefined. Okay, potential is undefined. Okay, for one body. Okay, potential is undefined for one body, in this case charge. Okay, so we can have the potential of two charges, we can have potential of three charges, but potential of one charge is, the question itself is wrong. Okay, now in order to get into what to say, the concept of a potential energy of a point charge, okay, we need to first of all understand what is potential energy, which we did in class 11. Okay, now actually in H.C. Verma book Concept of Physics, potential in physics, potential is not defined. Again, only thing which is defined is change in potential energy. Okay, change in potential energy is the negative of work done by the conservative force. This is the real definition of potential energy. See, again I'm repeating, potential energy is not defined. What is defined? This is the change in the potential energy. Change in the potential energy is defined, and that is what? That is a negative of the work done by the conservative force. One more thing, for a point charge, we cannot have potential energy. In order to have potential energy, minimum there need to be two charges. Okay, then only we can have a concept of potential energy. That also what? Change in potential energy. Understood? Okay, in this regard, let me just take one simple example where we took the gravitation, because in class 11 we studied about that. Okay, suppose let's say there are two heights. Okay, there are two heights. Let's say the height is of h1, okay, and the mass m1 has moved up to the height of h1. All right, so this mass have been moved up. All right, now what is the potential? Okay, let's say call this initial energy, potential energy u1, and let us call this uf. Okay, so what is the change in potential energy? Delta u is equal to final minus initial, right? And this is equal to, okay, potential energy, this is equal to what? Negative of work done by the conservative force. Conservative force here is a gravity, right? Now what is the work done? Minus work done is what? Force dot displacement, right? Isn't it? Which force it is? Gravitational force, right? So the negative is already there in the formula, so I have written down this. Now this is, what is the angle between F and S? Gravity is down, S it has moved up, right? height. Then this is what? Minus Fs, cos of how much? 180 degree, right? Now cos 180 degree is minus 1 already. Then minus Fs, this is minus 1, right? Now this is minus minus plus, force is what? Gravity, it's mg, and what is the height? h1, right? So in class 9 also, the potential, the raise in potential energy when the bodies rise from one height to another, actually that is the change in potential energy. I repeat, in physics, potential energy is not defined, only the change in potential energy is defined, and that is work done by the conservative force. In this case, the conservative force is gravity. In our next situation, the conservative force is the electrostatic force. Okay, so okay, now let us take now in your question in the syllabus, we call it as potential energy of two charges. Okay, one charge though it cannot have potential energy. Again I have said two charges, potential energy of two charges. Let's say now let's say here is q1 and let's say here is q2. Okay, let's say these are at the distance r away. All right, now potential energy of two charges, we said. Now let's say this is a final configuration, because we said, again I'm saying, change in potential energy is only defined. Okay, so we are going this way, indirect way. This is the final configuration. Let's say the initial configuration is, in the initial configuration, see this is indirect way. Okay, initial, in the initial configuration, let's assume that q1 and q2 are at infinity. All right, at infinity. So this way, so initial, they are at at infinity. Okay, and in the final configuration they are brought to the distance of r. Okay, now we know in at infinity, so this is, let's call this one as u final, and let's call this one u initial. Now infinity concept, what is the potential? Zero, right or not? Okay, so we always say that potential at infinity is zero. Similarly, potential energy at infinity is zero. So what is the change in the potential energy? Potential energy change is equal to u f minus ui. All these are indirect way we are doing it. All right, and this is equal to what? Minus work by what? What force? Electric force, electrostatic force, work done by the this one. Okay, all right, now this work done, electric force. Okay, so ultimately what we have, delta u is equal to what? Potential energy of this system, right? Okay, now this work done, okay, minus is already there. This work done is what? Work done, this is what? Work done in bringing q1, right, from infinity to here. Means when q1 is brought from infinity to here, what is the amount of work done, right? Another, what is the another work done? Work done, let me write it as w, in bringing whom? In bringing q2, right? Okay, so these are the work done. Means if I, for bringing q1, what is the work done? If I compute in bringing q2, what is the work done? If I compute, then what? That is the potential minus of that, right? Okay, now let me make this figure a little in a better proper way. Okay, in your notes also I have done the same way, you can follow. Okay, let's say, all right, q1. Okay, from infinity, okay, from infinity, let's say q1 have been brought. All right, how much is the work done? Is there is any force? No. If there is no force, will there be any work done? No, because we know that work is F dot S, right? Now F is how much? 0, right or not? So will there be any work done? No, there will be no work done. So this will be what? 0, right? Now another. Now from infinity, we are all doing all the work from infinity. Now what we are bringing? So Q1 has brought here already and 0 work is done, right? Now what? From infinity whom? Q2 is being brought, right? Q2 is being brought. Will there be any work done? Yes, there will be work done. Why? In order to bring Q2, we need to overcome the repulsive force due to Q1, right? That means external agency need to apply the force. Then only the Q2 can be moved up to this distance. This energy is stored as potential. Understood? So work done, work will be done, right? Work will be done. In this case, work done in bringing Q2 from what? From where? From infinity to R. Okay, from infinity to R. Okay, because work have to be done against the repulsive force, right? Okay, now how much it will be? So let me, in this case the force will be a variable. So when the force is a variable, we need to apply the concept of integration. We have already said, I will assume, as we did in the potential concept, I will consider a small distance PQ with the length of dl, so that the electric field is uniform over this length. It's very small. All right, then this will be what? The force is a variable, right? Force is a variable. So what I will do? Directly integration, right? So work done, this will be what? dw. From where? From infinity to R. Okay, then, all right, then this will be, what? This will be minus R. Work done is what? See, always the integration will be always holding correct. Now in this case, why we have gone through this integration? Because the force is a variable. As Q2 is far away, the force is lesser. As Q2 is approaching nearer the Q1, the force will be stronger, right? That's why. Then this will be what? F dot, right? This length we are considering. So what? This is dl. Now we have to go through the same technique. Now force is what? Against the repulsion. Against the repulsion, force have to be applied, and that force is what? Minus Q0E. No. Not Q0 is brought. Who is brought? Q2 is brought, right? Fine or not? So this have to be minus, there is integration to R. F is what? Against the repulsion, isn't it? So this will be Q2E dot of dl. Okay, now minus and minus, this will be plus. So this will be what? Infinity to R. What is the angle between E and dl? Okay, what is the angle between E and dl? E is along this side, D is along this side, right? So the angle between E and DL is 180 degree, right? Cos of 180 degree, fine. Then this will be what? I will not call any more delta U, because delta U is equal to UF, isn't it? Because UI is what? UI is 0, right? So this will be, I'll just write it U, and this is equal to what? EDL cos of 180 degree, and this is minus 1. So minus, this will be what? Integration to R, then this will be what? E. Now DL is along this side, right? DL is along this side, but our measurement is from here, right? So as we did in potential, we take DL as minus of dr. Okay. Okay, here is Q2. I forgot to write that. Okay, so here is Q2 here. Okay, then this will be what? Minus and minus will be plus, so this will be plus Q2. Then this is what? Integration to R EDR. Okay, now you can see the potential derivation at a point EDR, and it will be exactly the same. So what it will come, if you do that integration, this will come as Q2. This is, it will be same as that of the potential derivation for EDR for this step. Okay, so what it will be Q1 by 4 pi epsilon naught R. Okay, so we have the expression for potential for 2-point charges kept R away is K Q1 Q2 by R. Simple. Okay, fine. So you need to remember this derivation. Okay, now based on that, in the book I have discussed a number of questions. Okay, so you can see all the questions. Let's say let me take one. Let's say here is an equilateral triangle. Let's say here is an equilateral triangle where the three charges are kept Q, Q, Q. In the note also I have written, let's say equilateral triangle, so A, A, A. Now what is the potential energy of the system? Then the potential energy of a system for 2, let me call this as 1, let's call 2, let's call 3, right? For this 2, the potential, let's call 1, 2, right? It's a scalar quantity, so we don't need to bother about the direction. 2, 3, and for this is what? 1, 3, right? System for this, and for this, right? Then this will be what? K Q by what is that? How far away? A, right? Then all of them will be the same, right? So K Q by A, ultimately what is the potential energy? This is 3 K Q by A. So you can have a look on the rest of the numericals based on potential. Thank you.